Hello, I'm David Domingo, and I'm here to present our work, pFSCK, a system built towards making file system checking faster and easier to bear with. This is work that I've done with my advisor, Sudarsun Kannan, here at Rutgers University. So I'd like to start off by walking you through a situation. This is you, and this is your computer. This is where you run very important applications and research things. However, you're going to have to reboot your computer due to a kernel upgrade, security patches, or even worse, a crash. Upon rebooting, you find out that your system can't start up because there's some issues with your storage device. So what do you do now? Unfortunately, you have no choice but to run the file system checker. However, you find out it takes way longer than you expect, resulting in a large downtime and decreased productivity. A few months later, after you resolved your issue, you save up some money to upgrade your system with faster modern storage in hopes that file system checking won't take as long in the future. Eventually, errors come up, requiring you to run the file system checker, which runs slightly faster, but it's still painful to use. You know you should probably run the file system checker more proactively, but are hesitant because that means more frequent downtimes. Based on your horrific experiences, you ask yourself, why? Why me? So you take to the internet only to find out that you're actually not alone, and this has been an issue for years. And this is where pFSCK comes in. pFSCK provides faster checking runtimes in order to make file system checking less painful. And it does this by parallelizing checking at a finer granularity, such as inodes, ensuring correctness through logical reordering, and adapting to file system configurations with dynamic thread scheduling. In our experiments, we find out that pFSCK shows up to 2.6 times improvement over E2FSCK and 1.8 to 8 times improvement over XFS repair. So on to a little background. I first want to start off with a background in storage reliability. First, file system checkers can be used after critical events in order to provide ultimate data reliability, but these checkers remain unoptimized with notorious runtimes discouraging good storage practices. Second, faster modern storage can be used to speed up file system checking, but high-density storage devices are still prone to cellware and bit corruption. Lastly, modern consistency mechanisms such as journaling, copy on write, erasure coding, and replication can be used to mitigate the use of checkers, but mechanisms such as journaling and copy on write can detect silent bit corruptions, reconstructions and resharding needing for erasure coding takes time, and finally, replication is not always economically feasible. This is to say, traditional file system checking is still relevant. So a little background on file systems and how they're checked. This is Linux's ext file system layout. An ext file system consists of multiple block groups, and each group is split up into 6 sections: the superblock, the group descriptor, block bitmap, inode bitmap, inode table, and data blocks. In order to verify consistency, ext's file system checker E2FSCK scans through the metadata of every block group and builds its own view of the file system in order to detect and fix inconsistencies. The checker itself consists of 5 logical passes: the inodes pass, which checks the consistency of inode structures, the directories pass, which checks directory metadata, the connectivity pass, which checks all files are reachable from the root, the ref counts pass, which verifies link counts, and finally, the cylinders pass, which verifies the stored cylinder group information. So there currently exist a few approaches that aim to improve the way file system checking performs. Currently used file system checkers such as E2FSCK and XFS repair can parallelize checking on a coarse granularity such as disks or groups. More modern approaches such as FFSCK, chunkfs, and squick also aim to optimize performance, but they either require an extensive modification to the file system or a complete overhaul to the file system checker. So, in order to motivate our requirements for an optimized checker, we first take a look at E2FSCK's current performance and complexity. To do this, we took a system with 64 gigabytes of memory and a 1 terabyte NVMe flash storage device. We then run E2FSCK against an 840 gigabyte file system of varying configurations. For the first set of configurations, we varied the file count, keeping the file size constant. For the second set of configurations, we varied the directory count, with each directory having 1 file. So first, let's take a look at how E2FSCK performs with varying file counts. On the x-axis, we have file count in millions, and on the y-axis, we have the runtime. We break down each runtime according to the different passes. We see that as we increase the file count, that the runtime increases quite a bit. Looking at the directory count, we also see a similar trend, but with larger runtimes. In the end, we see that the majority of time is spent checking inode and directory metadata. We also see that directory-intensive file systems take significantly longer to check than file-intensive file systems, and ultimately, we see that runtime scales linearly with file system utilization. Based on this analysis, we ask, how can we speed up file system checking and repair without compromising correctness? And how can we adapt for differing file system configurations, for example, file-intensive versus directory-intensive? So pFSCK answers these questions by parallelizing file system checking at a finer granularity, such as inodes or directories. And in order to allow for this, pFSCK overlaps as much independent logical checks within each pass, overlap as much logical checks across passes, minimizes contention on shared data structures, and lastly, efficiently manages work for threads operating across passes. Now, onto pFSCK's design. Before we get into it, let's first take a look at the serial execution of E2FSCK. Within each pass, E2FSCK serially checks file system metadata, for example, inodes in the inodes pass. And while it does this, it updates global data structures that maintain the checker's view of the file system. Lastly, E2FSCK generates works for the next pass, for example, directory blocks to check in the directories pass. In pFSCK, execution is improved with data parallelism. With data parallelism, metadata needing to be checked within a pass is split into smaller groups. A pool of threads is then used to check these groups in parallel and generate intermediate lists. These lists are then aggregated, and the process repeats in the next pass. However, there are still some data structures that can't be isolated without significant changes. For example, a global block bitmap is required to detect whether a block is referenced by multiple inodes. Because of serialized accesses to these global data structures, this in turn limits the amount of concurrency we can achieve in a single pass. In order to combat this, pFSCK hides synchronization bottlenecks by introducing what we call pipeline parallelism. With pipeline parallelism, pFSCK allows multiple passes to execute in parallel. In order to do this, pFSCK first turns each pass into independent flows of execution, and then it assigns a metadata queue and a thread pool to each pass. By doing this, pFSCK enables previous passes to continuously feed metadata needing to be checked to the next pass, allowing the subsequent pass to speculatively carry out future checks even before the previous pass has finished. However, even with pipeline parallelism, we still face the issue of work imbalance. In this case, differing metadata densities would cause uneven pass queues. Because of this is not straightforward how many threads to assign to each pass. For example, a directory-intensive file system may have more directory metadata to check, but we may have naively assigned more threads to the inodes pass. To solve this, pFSCK employs a dynamic thread scheduler. The scheduler periodically samples the work to be done in each pass. With this, it calculates the relative work among the passes and redistributes the threads. In the end, this allows pFSCK to adapt to differing file system configurations. pFSCK also includes other features such as support for online checking and error handling, which you can read more about in our paper. Now onto evaluation. In order to evaluate the benefits of pFSCK, we used a system with 64 gigabytes of memory and a 1 terabyte NVMe flash storage device, and we compared the following tools: E2FSCK, XFS repair, and finally pFSCK, our proposed system. For brevity, we'll only be showing the performance for a file-intensive file system. First, we want to evaluate pFSCK's data parallelism compared to E2FSCK and XFS repair. Here, on the x-axis, we have the different checkers with different thread counts, and on the y-axis, we have the runtimes. First, we have E2FSCK running serially with one thread. Next, we have pFSCK data para, which is pFSCK utilizing data parallelism with multiple threads. And finally, XFS repair, which uses threads to check allocation groups in parallel. First, we see that data parallelism improves performance by up to 1.9 times over the vanilla E2FSCK. We also see that pFSCK improves performance by up to 8 times over XFS repair because unfortunately XFS repair is unable to verify directory information in parallel. Lastly, we see that scaling data parallelism within pFSCK is limited due to contention on shared data structures. Next, we evaluate pFSCK's pipeline parallelism and dynamic thread scheduler. Here, we want to see how effective is pFSCK's pipeline parallelism and dynamic thread scheduling compared to just data parallelism. Here on the x-axis, we have the different checkers with different thread counts, and on the y-axis, we have the runtime. First, we have E2FSCK running serially with one thread, pFSCK with data parallelism, pFSCK pipeline, which is pFSCK utilizing pipeline parallelism running with the best case manual thread assignment, and finally, pFSCK Schedge, which is pFSCK running with the dynamic thread scheduler that automatically handles thread assignment. First, we see that pFSCK's pipeline parallelism increases performance by up to 1.3 times over just data parallelism. Next, we also see that the dynamic thread scheduler is able to automatically match the best case pipeline thread assignment, ultimately, in the end, improving performance by up to 2.6 times over the vanilla E2FSCK without any manual configuration. If you would like to see more evaluation, I'd like to direct you to our paper, which goes into more detail. To sum up, pFSCK provides fine-grained parallelism for file system checking. Data parallelism allows for more metadata to be checked at a time, while pipeline parallelism overcomes any data parallelism bottlenecks. Finally, the dynamic thread scheduler allows for automatically adapting to any file system configuration. In the end, this allows pFSCK to provide up to 2.6 times performance over E2FSCK. I'd like to give a special thanks to the FAST committee and our shepherd, Dean Hildebrand, for their great feedback and guidance. Thank you for listening.